You're muted.
We can go whenever. So go ahead and make your announcements.
Okay, is Yaroslav there?
I'm here. Yeah, I'm here.
All right. Well, then you can pause and okay. Great. Well, it's my pleasure to start the last session. I'm not chairing the last session, but I wanted to begin first by thanking the all of the wonderful people here in Copenhagen who really made this possible. And I know it was a virtual conference, but I think it went as smoothly as it possibly could, and it's due in large part to these people and some of the people who already are watching from home tonight. Anyway, I want to thank also the all of you for coming and participating. The talks were really amazing, and I'm really looking forward to Lance's summary of it. But before we get started, before we get underway, I wanted to first introduce Yaroslav Trenka, who has some very good news to share with us. And that didn't work, did it? No, let's see, how does this work?
Well, let me do it then.
Yeah, all right, I'm just sharing my whole screen. That doesn't seem to work. Go ahead.
Okay, so the next year, Amplitudes 2022 will be in Prague in August, possibly with the PhD school prior to the conference. It will be right after the MIAP program in Munich on developments in scattering amplitudes that some of you will probably attend. And the real local organizer, the main organizer, will be Karol Kamp, who will say a few words.
Hello, everybody. I am really quite honored and pleased that next Amplitude meeting will be organized by our university here in Prague. Yes, let me just add that we agreed very quickly with Yaroslav that we want to organize not only this conference, but also the school. We thought that especially now after this COVID break, it would be important, particularly for younger people, to meet in person with their peers. So, well, let's hope that we will really meet in person in August 2022. And before I give the word back to Yaroslav, let me thank Jake and all people in Copenhagen for a wonderful conference. Thank you.
Okay, thanks. I would also like to thank Jake and all the Copenhagen organizers, and Andrew will chair the last session.
All right, thanks, Yara, for that exciting news. Something for us all to look forward to. But now it's my pleasure to introduce our last speaker for the conference, Lance Dixon, who's going to give us a summary and an outlook talk. So Lance, please take it away.
Thank you very much, Andrew. Can you see my slides?
Yes, we can.
Well, we've made it, almost. Just one more talk to go before you can all get on your planes. Oh, sorry. Anyway, it's been an incredible week. There's been so many fantastic talks at this conference, and the ability to meet people on the beach in Gathertown has also been terrific. Now we did miss a few things. We missed being able to come to the Niels Bohr Institute. We missed a lot of the things to do in Copenhagen. But Jake tried to ease it on us by letting us know that actually it was rainy in Copenhagen much of the week. So thank you, Jake. But actually, I think we all need to unmute ourselves and thank these guys, Jake, Paul, Matthias, Matt, Emil, Michelle, and Andrew, for putting on such an incredible conference. Can we all give them a round of applause, please? It's hard enough when it's a normal conference. It's hard when it's a Zoom conference, and it's even harder still when you don't even know if it's going to be a Zoom conference or a regular conference. So you have to do all the planning for both options. And it's great that they came together and were so well organized. I also wanted to mention that, as I understand it, many students also contributed to getting all the talks up and online and things like that. So thank you to all of you. That was really fantastic work. By the way, some of you guys may not know that this is Jake here. He looks a little bit different in this picture, whereas Matt looks exactly the same. So I'd like to dive in now, but I wanted to give some apologies in advance. I may not be able to cover all the talks. In fact, I know I won't. And so apologies if I don't cover your favorite topic or speaker. So there are a couple of reasons why that might be. Like, some of the sessions started at 4 in the morning, California time. And although Jake offered to fly me to Copenhagen, I just couldn't justify it in the end. So also I just ran out of time too. So many things are, maybe you may find things still under construction in this talk, we'll see. And I'd like to also paraphrase Thibaut Damour, who is quoting Henri Poincaré. Maybe he also said, a summary talk is never finished, it is only more or less finished when the time comes to give it. So I noticed that Zvi gave a version of this slide earlier, so I tried not to touch mine after I saw his, in order that you guys can deconstruct whether his brain works the same as mine or not. But this is sort of how I see amplitudes and the kinds of connections it makes to other fields. And just as Zvi thinks, I think these connections are incredibly important and what give the vitality to the field. And as I was making this, I also realized I left off some other important connections, like integrability. That's another field of mathematical physics which overlaps very heavily with some of the things I'm doing. I just forgot to put it on here. But you know, a lot of the origin of amplitudes, as we heard from Zvi, was in QCD, and also a lot of the ideas of string theory were extremely important in going that way. And there was also a connection to gravity through there. And then other of these directions that developed more recently, like standard model effective theory, or applying it to nonlinear sigma models and chiral perturbation theory, holography. We heard about fluids from Cindy Keeler. And then there are the mathematical directions that people have gone in. But in general, having these links to the outside is incredibly important. For me, it's always very important when we can touch something that has something to do with experiment. I mean, that's what drove me to kind of leave string theory for what later became amplitudes in the first place, was wanting to make some close contact with experiment. And on the other side, we also have experiment. It's experimental mathematics. We try out mathematics. If it works, we keep it. If it doesn't work, we throw it out and move on. And I think there's a huge amount of vitality in importing ideas from mathematics, maybe even working with mathematicians who are developing new cutting edge mathematics. So that's another vital area of our enterprise. I found this quote recently from Yukawa, and it really resonates with me a lot in the kinds of, especially literally in some of the things I've been doing recently. And it says that those who explore an unknown world are travelers without a map. And the map is the result of the exploration. The position of their destination isn't known to them, and the direct path that leads to it is not yet made. So our job is to do this exploration and to connect back eventually to other areas of the known world. And it's no fun if there aren't dragons somewhere, you know. So just want to remember a great physicist who passed away less than a month ago, because he was an incredible explorer who guided many theoretical physicists on their journey. To start with, he gave us SU2 cross U1 and gauge theory. And of course, gauge theory is a launching point for many of the things seen in amplitudes. But that wasn't all. He also gave us EFTs. He went from current algebra and soft pions in the early 60s to the nonlinear sigma model Lagrangian. And you can read a quote from him from much later on about how the most convenient way of implementing all the S-matrix assumptions was by good old quantum field theory, which the S-matrix theorists had hoped to supplant. Well, some of us are still trying to supplant it or reformulate it back in terms of S-matrix language, as you can see in the talks by Shadmi, Machado, Wang, Karen Hua, Rosen. So he had a huge impact on this field in that way too. And if you listen to the talks, the number of times you heard about Weinberg's soft graviton theorems was more than the ones I listed here, but I can't remember all of them, in fact. So we heard about it in these talks, for example. And another person we lost not a little bit longer ago, in fact, before the last in-person Amplitudes in Dublin, was Murray Gell-Mann. And he was another giant of the 60s and 70s. And he gave us SU3, not SU2 cross U1, but he gave us not just one SU3, but two of them, both color SU3, well, flavor SU3 first, and later he was instrumental in deciding that the right non-abelian gauge group was SU3 color for QCD. So I think if he had been listening to this conference, he would have really loved the gauged by adjoint scalar theory, since it's got that flavor and color, albeit in somewhat different representations than quarks, but close enough. And then another giant of 20th century physics who did attend this conference and actually welcomed us to it was Niels Bohr. And Niels gave a great greeting to everyone coming virtually to Copenhagen, although he does seem a lot like Yoda to me, but okay, then maybe that's just me. But of course, Bohr gave us many things that are extremely critical for all our thinking: the wave-particle duality, the fact that you can, and even more generally, hold together two contradictory things in one hand, like you can read this as light as a particle or light as a wave, and understanding both implications at the same time is critical to making progress. And in particular, this going back and forth between wave and particle pictures is critical to the scattering amplitude for LIGO picture. Some of this was also emphasized in Thibaut Damour's talk. And of course, also the correspondence and the classical limit and so on. And finally, there's Richard Feynman. And he gave us Feynman diagrams. And as Sebastian mentioned, maybe the first Feynman diagram was actually due to Stuckelberg. And we often try hard now to avoid saying that we use Feynman diagrams, but you can see them popping up here and there throughout the talks. And if nothing else, they certainly characterize what classes of things people are looking at, even if we do things now where the number of Feynman diagrams would be ridiculously large. But of course, another thing that came along with Feynman diagrams was relativistic causality and its implementation through the Feynman propagator and its I epsilon. And that, of course, plays a critical role in many more general analyses, which aren't necessarily even diagram based or based on infinite numbers of diagrams. So I epsilon is always there behind the scenes, and you can sometimes run, for example, to Euclidean regions of kinematics, of planar theories, and positive regions of Grassmannians, but in the end, you can't hide from I epsilon. And finally, he gave us, or the class of things we consider now in higher loop perturbation theory, are Feynman integrals. And that's the gift that keeps giving. There will never not be a Feynman integral to do out there. And I think this is number one for the great superset of topics that we heard about here. The difficulties of doing Feynman integrals and how to surmount them was present in talks by Langer, Clem, Mazzara, Badger, Volovich, Zung, Weinzierl, Brown, Zhang, Signorilla, Dur, Brito. And it was under the hood of many other talks, for example, Misselberger, Vita, Damour, Heisenberg, Solon, and I haven't even necessarily categorized these all right. And Feynman integrals were became Feynman polytopes in Nema's hands. So now let's talk about a few specific things we saw. I was going to title this slide Albrecht and Claude Go Bananas, but I thought this was slightly more polite. So I just decided this is Bananarama. And what they were telling us about is the close connection between higher loop integrals and Calabi-Yau geometries. Many aspects of this are already known to some of the organizers of this conference in particular, but they made a very complete map for the case of the banana integrals of an arbitrary number of loops. And they also have a statement that because these Calabi-Yaus that are associated with the singularities in the Feynman integrals are often themselves singular varieties, it could be better to associate them not with single Calabi-Yaus, but with families of Calabi-Yau motives that have sort of a compatible Hodge structure and Galois group action. So that seems extremely interesting, as well as the fact that they could get very good numerical results out in single variable examples. We also heard today, or had a little advantage in having seen the paper before, about the elliptic double box, which was a much more concrete representation of an example that has been long known to the n=4 super-Yang-Mills community. This is the first place that planar n=4 super-Yang-Mills becomes elliptic. And Zhang and collaborators were able to sort of integrate this integral explicitly in terms of elliptic polylogarithms. And there was an earlier differential equation for this sourced by a d=6 hexagon. And they noticed how when they computed a symbol for this quantity that it has, that this structure of the differential equation tells you that the ellipticity of the alphabet, the elliptic letters only show up later on in the symbol in the last two of the entries. We also heard from Stefan Weinzierl, and he discussed more general classes of elliptic integrals and the fact that for numerical purposes, it's very handy to apply the modular symmetries or transformations in order to move the parameter describing the torus into a fundamental region of the modular group. And then the Q expansions converge extremely rapidly, but there are subtleties in doing this, which he discussed. Now I want to mention something close to my own heart, which is unitarity as a tool. And it's a kind of a carving knife. Often when you have a complicated problem, the way you beat it in submission is by chopping it into little pieces. And so it sort of used to only be good for slicing up integrands. And in some sense, it's still good. We heard from talks by Simon Badger and Michael Salone, how to organize integrands in terms of cuts. We also heard from Cameron Langer about a prescriptive variant of generalized unitarity that separates out the different contributions more cleanly. So it's a little cleaner slice where you use chiral traces in the numerator and how cleanly that works at two loops. But this unitarity knife, it also carves in reverse. In other words, if you have a case where you actually want to cut in an integral because it's a phase space constraint, and you reinterpret it as a imaginary part of a propagator, then you can exploit that and turn cut integrals back into things that look almost like integrals. And that allows you to do phase space integrals, especially in cases where they can be done analytically. We heard about that in the context of the talk by Signorilla and Signorilli about the kinds of integrals that you need to do in order to integrate subtraction terms in computations with flexible experimental cuts. You are always doing complicated integrals of various splitting functions and things like that. And she discussed how to do that. But it also comes up in the when you try to calculate, for example, the radiated momentum in a binary in spiral from the formalism developed by Kossauer, Mabey, and O'Connell, you have to do phase space integrals. And as Zheng was describing, you can also do those by reverse unitarity. But in addition, unitarity in a much different form has become a really excellent tool these days, along with causality, crossing symmetry, Hankel matrices, and linear programming for carving another kind of carving up the space of effective field theories. So we heard talks by Yutin Huang and Simone Caron-Hua about scalars both without gravity and with gravity, and isolating regions of the parameter space of the higher dimension operators that are allowed when you apply all of these different principles of quantum field theory to limit what the possibilities are for effective field theory contributions or coefficients. We also heard about Sebastian Mazera. He gave us a beautiful proof of crossing symmetry in which you've got to track those I epsilons very carefully. And he developed a clever path through the space of momenta, starting with real momenta and ending up with real momenta. And that, combined with a number of other slick manipulations, allowed him to argue for to give a proof of crossing symmetry. It's perturbative, so it's not fully non-perturbative, and it's also in the context of large N or planar diagrams, but otherwise it's very general, and I'm sure there's more to come from this in the future. The double copy was another major theme of this conference. The double copy began, as we heard in Zvi's talk, in the 80s with KLT, and we had a slogan in the 90s that gravity was the square of Yang-Mills theory, which we would utter to anyone who wanted to hear. But with the work of BCJ in 2008 and 2010, it became more than a slogan. It became, well, it was more than a slogan before. The KLT relations were always there, but it was reformulated in a graphical fashion, as in this slide from Ingrid Vasquez-Holmes' talk. And of course, it became much more general than just gravity equals Ym squared. It's now, it now connects a much broader web of theories. And it also underlies, in the original formulation or application, it underlies much of the motivation for the scattering amplitudes for LIGO program that we heard about. Now, one of the double copy talks we heard was by Henrietta Elvong, and she discussed how to try to generalize the rules for double copying by changing this kernel, the KLT kernel that sits in between the left and the right amplitude. And so she pointed out that there's a KLT algebra and there's an identity in the algebra. And this relation is a key relation that gives you bootstrap and constrains what you can do. And she and her collaborators found new solutions for this KLT kernel that go beyond what you can do when you try to apply just a field theory KLT to higher dimensional operators added to Yang-Mills theory. So there are certain operators that you can't make consistent with the double copy without performing this generalization. So this opens some new avenues for more progress in the direction of connecting various theories. Another very interesting talk was by Cliff Chung, and he took quite novel, with his collaborator James Mangan, quite novel approach in looking at field equations for field strengths and observing that in the structure of the field equations, there's just a direct map that allows you to derive types of double copies. So one version was what he called the nonlinear sigma model, tensor nonlinear sigma model map. And in that case, there's just a set of fully off shell with these. So there's in the solving the field equations, there's always a root leg, which is like the current in the Behrens-Gila construction of one off shell rest on shell legs. But these guys don't need to be on shell yet. They could still be splitting further down the road. But there is still one leg that's singled out, and there's an orientation to these vertices here. But these relations satisfy the color kinematics relations, ns plus nt plus nu equals 0 for any values of the momenta flowing through these black blobs. So this is a pretty, and when you apply a similar one to try to generate Yang-Mills, you find that Yang-Mills itself is a double copy of the gauged biadjoint scalar theory we talked about before, but with a different tensoring, the F-cube tensoring. And but by using that and various tricks, he was able to write down, they were able to write down closed form expressions for BCJ numerators. So this is, I think, a really new perspective on color kinematics duality and the double copy. It's explicitly been done for classical equations of motion, but it certainly, of course, begs to be applied at the loop level in the future. The double copy with masses was the subject of a few talks. Shruti Paranjape argued that for the double copy with masses inserted to be local, there were two options that could be followed. One is where you cancel spurious poles using special properties of the amplitudes themselves. And then the other one is that the spurious poles in the KLT kernel cancel themselves, but only when the masses are carefully tuned. And option one seemed to work for DRGT massive gravity, but only at 4 point and not at 5 points. This is, okay, my failure to understand this by the time I had to give this talk. Option two was satisfied for toroidal-Kaluza-Klein compactifications, but I think it would be very interesting to investigate further if there are other solutions. And I'm not sure where that's heading, but I think it's an interesting future direction to follow. There is also double copy with scalar masses as opposed to vector masses, which was discussed in the talk by Vasquez-Holm. And they particularly gave this example at loop level and 5 points, where if you double copy a gauge theory with massive scalars, you can get massive particles and loop level gravity, which is obviously motivated by problems in black hole in spiral radiation. And so they applied maximal cuts and took out these unwanted dilaton and axions by hand through this projective double copy. There was another double copy in the sky, and I could only think that this celestial diamonds must have been paying tribute to another group or song from the Beatles. But this was a discussion, and I was not able to get up early enough for the talk, so I'm a little behind there, but it involved this map of soft emission onto a celestial sphere, since when you make soft emission, there's a characteristic energy scaling, and other than that, overall energy scaling, things really only depend on the angles. And there were also a similar, there was a talk by Kalyana Puram, which was also analyzing soft behavior in this 2D sky. And the massive soft limits were discussed by Machado. The first talk at the conference by Yvonne Geyer was also at 4 a.m. California time, but fortunately she summarized her results in a single slide, which I could crib here. And they have a very interesting proposal for importing field theory results and lifting them back up and giving proposals for what full string integrands are. And this is pretty amazing. It works through 2 loops. And if it continued to work at the 3 loop level, where I think there's still some questions about uniqueness that she mentioned, it would be really fascinating if field theory has enough information to reconstruct string theory. As V mentioned in his reminiscences, he and David Kossauer worked really hard to get rid of the string theory. If it's all sort of hiding there in the background to be reconstructed, that would be rather amusing and amazing. So Yael Shadmi discussed how to do aspects of the SMEFT program for constraining physics beyond the standard model at colliders through the standard model effective field theory. I think this is a great new arena where amplitudes can contact experiment at colliders besides QCD. Can also be applied to other areas besides collider physics, obviously. EFTs are often used in flavor physics as well. So both massless and massive versions of EFT were discussed in her talk, and the latter case leverages some massive spinner technology that was developed by Arkani Hamid, Huang, and Yael discussed bolding as Higgsing. That is mapping from a massless EFT to the massive EFT by using a bolding operation first defined by AHH. So that's a pretty, there are a lot of interesting developments in this direction. It's clearly going to be very active in the future. Now, of course, we also had talks that were more mathematical in nature, for example, discussing the geometry of amplitudes. And there was a talk by Matteo Parisi on the hypersimplex as a sort of polytopic type structure that is T-dual to the amplituhedron. And of course, Arkani Nima gave us a Nemathon a few nights ago, in which he took trace of phi cube theory and processed it in many different directions, so that it now looks very much like string theory, but string theory plus many infinite dimensional polytopes. Now, usually during a pandemic, you talk about turning a negative into a positive, but Yara was going back the other way, and he turned a positive into a negative in terms of geometry. So he described how you could reclassify positivity constraints shown in these dashed lines and rewrite them as things that are decoupled plus negative constraints. And by summing over all graphs and also by taking logarithms, he arrived at only connected graphs in terms of these negative quantities. And then he and his collaborators, Johannes Henn and Nima, they analyzed in this way a very interesting quantity, which is the function of a square Wilson loop, but with an insertion of an extra operator. And there's a single conformally invariant cross ratio that you can write down. And you normalize by the thing without the insertion in order to cancel out the singularities, the cusps. And this quantity, they can study it in perturbation theory, and then they can also resum it in various tree and ladder approximations. So the tree approximation, in fact, they found this closed form expression for the regulated version of it in terms of a transcendentally defined quantity. And they also analyzed its perturbative behavior and strong coupling behavior. And it's quite close to, at least for the cusp that I remember, quite close to the full result. So that's pretty interesting and could even be the basis of a future way of reorganizing a series and so on. So now we're going to take a little break from the mathematics and go to the physics at the LHC, the world's only Higgs factory these days. And the Higgs lies at the very center of the standard model. And one of the ways of testing the standard model, and in particular the electroweak sector, which still puzzles us some, why the Higgs is so light, or the electroweak scale is so light compared to, say, the Planck scale. Also, the Higgs is a very funny beast. Not only is it the only scalar, but it's the particle that makes the most connections to other particles. It connects directly to every other particle in the standard model, except, well, the neutrinos, it talks through it, except for the photon and the gluons. But ironically, it actually does talk to the gluons quite a lot through virtual loops. of top quarks. Anyway, it's extremely important to understand the Higgs boson. We need to understand if that Higgs is exactly the one predicted by the standard model. There are various operators that you could add involving Higgses and other fields that are portals to new physics. So there's a chance that we could see new physics first in the Higgs sector. So we need to get a good profile of the Higgs boson a little bit better than this observation here, that it was definitely the Higgs. So we need to measure its properties. The mass has already been measured extremely accurately. The problem is that it's not predicted by the standard model. So it doesn't really lead to any possible breakdown of the standard model to improve its precision. The spin is 0, and that has been checked quite carefully by the LHC experiments. So we got that one right, or the standard model got that one right. We also need to know how often it's produced, the cross section, and as well the branching fractions to all final states. That is its couplings to all the fermions and bosons in the standard model. Now there's a little problem at the LHC that you're only able to measure the final states, and you can only measure the product of the production cross section times the branching fraction. That's what gives you the final event yield. And so at the LHC, there's a huge premium placed on understanding this cross section directly. Experimentalists only see this product. They can't do anything about measuring couplings through branching fractions, and also there are couplings in the cross section, unless they know the theory uncertainty. So we heard from Bernard Misselberger about the incredible advances in precision that have been made on this dominant production cross section. There are several ways of making the Higgs boson, but 2 gluons through a top quark loop to a Higgs is the dominant cross section, and it's incredibly badly behaved in perturbation theory. So the leading order expression is off by much more than a factor of 2, maybe close to a factor of 3. And even NLO and NNLO do not have very good overlap. But thanks to he and his collaborators' work on the N3LO cross section, we now have, there are now predictions from theory, which when you include all the other uncertainties are comparable to the experimental measurements. And that result was a couple of years back, but more recently, Bernard and collaborators have been applying similar technology to the production of another color singlet object, which is an electroweak vector boson like a Z. And in early 2000, they did the Drell-Yan case, and these results are more hot off the press, including the full Z resonance line shape and a number of annoying quantities that actually don't change these curves very much. So this shows the Q squared, or the square root of Q squared of the invariant mass of the lepton pairs. And I worked on aspects of this back at NNLO, and you can see that the NNLO band is really not close to the truth now that the N cubed LO is available. Now, the precision here is extremely, is way below 1%, or is significantly below 1%. And also, this does not yet include N cubed LO PDF evolution, which I think is likely to be much more important here than in the Higgs case. And what's definitely important for turning this into confrontation with experiment is to include experimental cuts. I should say that the statistics on these is much higher than the Higgs statistics. And so experiment can achieve incredible precision. And this is one of the ways of constraining the partons inside the proton that go into predicting all LHC processes. So further advances here are going to make a big difference in that. And some of those advances were talked about in the talk by Gerardo Vita. He described a collinear expansion of cross sections. And these are cross sections where you make a constraint that all the partons that are radiated, instead of it being totally inclusive about where they go, you require them to all go parallel to the beam direction. And there are many applications for this requirement. He showed us one, which was the energy-energy correlator in the back-to-back region and resumming it. But also a very important, another application is that some of the elements that you develop with this technology, certain beam functions, can be used to make the N3LO computations more differential and thereby implement actual experimental cuts. So Bernard showed the N3LO revolution in progress, and some of it is being enabled by going more differential down in this region by these underlying developments. So that's basically it for the LHC, and now we're going to switch to the greater universe, in particular to black hole physics as viewed by LIGO Virgo. And I just wanted to remind you of this quote by Chandrasekhar back in 1979. He remarked that the black holes of nature are the most perfect macroscopic objects that there are in the universe, because the only elements in their construction are our concepts of space and time. And I like to think that scattering amplitudes are a microscopic map of this statement, that they're the most perfect microscopic objects we can imagine. They're smooth functions of the external data and very little else. And it's really remarkable that we can use them to describe not only the shortest distance physics that we can access experimentally at the LHC, but also incredibly long distance physics happening in the universe at large. And we heard several talks on the application to black hole physics of amplitude type ideas. Here's the binary in spiral and this is the kind of waveform that LIGO sees, obviously with a lot more noise when it actually sees it. I just wanted to remind you all of the scales involved. We can plot the center of mass energy at the LHC in units of the Planck scale. And since it's at 14 TeV and the Planck scale is at 10 to the 19th GeV, there's about 15 orders of magnitude to go to reach the Planck scale. On the other hand, the mass of the sun is 10 to the 38 in Planck units. And so roughly the LIGO Virgo center of mass energies are up here around 10 to the 38 to 10 to the 40. But center of mass energy isn't everything. There's also the impact parameter. And in that case, everybody's at distances much larger than the Planck scale. I put the impact parameter in the denominator. So this would be if you had a Planck scale collider. At the LHC, we're 15 orders of magnitude off. The LHC is very broadband in impact parameter if you count the forward detectors that see the elastic scattering. So I drew a big blob here, and LIGO is not quite as broadband. Anyway, they occupy impact parameters that are 20 orders of magnitude bigger than the LHC. Now, the interesting development that's happened over the past few years, and I think some of this was anticipated and discussed by Thibaut Damour a while ago, slightly before Amplitudes people started coming in, is that you can learn a lot about the in-spiral problem from black hole scattering. And also, I think some of this was anticipated by Chung, Rothstein, and Solon, and Goldberger and Rothstein earlier, because the scattering problem and the in-spiral problem, when they're very far out, you can just see it's almost exactly the same process. It's just one slightly above E equals 0 and the other is slightly below. So because they're so close to each other physically, there's a kind of analytic continuation around R equals infinity. One way of accomplishing this map, going from scattering, which is what Amplitudes people like to do, to in-spiral, is via an effective Hamiltonian. But then there's also work that does it directly in terms of trajectories by Kalin and Porto. And the nice thing is that you have more dials in the scattering problem. And so you can diagnose things and understand issues in the in the higher orders of gravity, since they're extremely complex, by adding these extra dials to tune. So we heard more specifically about a number of different approaches to try to get to high orders. Damour discussed how his work with Bini and Geralico has added many ingredients so that the 5th post-Newtonian level is almost there, up to 2 undetermined parameters. And we also, there are other complementary approaches. We heard about the on-shell approaches in the talks by Zhang and Solon, and there are also world-line approaches that have been working hard at both post-Newtonian and post-Minkowskian order. So we saw a similar plot to this, I think, in Michael Solon's talk. And it just shows the progress over the centuries in the post-Newtonian expansion, which is a combined expansion in G and the velocity squared, versus the post-Newtonian, which is just an expansion in G Newton. And well, Newton was 0 PN, so he was about a couple hundred years before the next PN. That had to wait for Einstein. But anyway, in the past year or so, we've had further advances. First, there was 2 years ago, there was progress at 3 PM, and there's been a lot of work on these pieces of 5 PN, partly from Blumlein, Meyer, Marquardt, and Schaefer, as well as this work I mentioned earlier by Damour and collaborators. And then the 4 PM result was discussed in talks at this conference by Zhang and Solon. And this new state of the art for PM is, of course, very interesting from an analytic point of view. These arc caches are secretly logarithms, as I recall, or close to that. So most of the stuff here is what aficionados of polylogs would say is not as interesting. We've seen those functions before, but of course, many in the audience have also seen elliptic integrals before, but this is the first time they've shown up in the PM expansion. So that's a interesting development and presages perhaps even more complicated functions to come at 5 PM. Now this result was missing a tail contribution here. This is just the finite part. But even if you ignore this tail contribution, you can compare and apply these results within the effective one-body framework. And this is just a reminder that this framework, which was also mentioned by Damour, was inspired by QED bound states, and it interpolates information from various sources. So it can be, it's phenomenological, but it can be improved as you insert additional information, either post-Newtonian or large ratios of the masses, and they even know how to get the PM information into it. And it's really the state of the art for accurate gravitational wave templates when you need to scan a wide variety of parameter space, because it's much faster than numerical relativity. And in Michael Solon's talk, we saw the impact of looking at this 4 PM contribution. And this is quite dramatic to me, the fact that when you're at 3 PM, you deviate from numerical relativity quite early, say around, this is the in spiral is coming down this way, so the velocity is increasing as you in time, and you peel off here at 0.03 or something, but now you can get out to about 0.05 or something, and the fully 4 PN consistent EOB is not really that much better until you get out to about here. And also the 4 PM, as I understand it, has started to be incorporated into the EOB. And at this point, the results are fairly similar to the 4 PN improved EOB. Okay, so that's it for LIGO. Now we're moving to an area which is close to my heart in the sense of what I've been working on recently, but it's the structure of amplitudes in planar n = 4 Super-Yang-Mills theory. And we heard from Anastasia Volovich about new ways to try to diagnose their structure. In particular, you can define the symbols of polylogarithmic functions. And if you want to know what they look like roughly, you need to know the symbol alphabet. And there are square root letters that develop at the 8-point level. At the 6 and 7-point level, thanks to Anastasia and her colleagues' work, we sort of understand what that alphabet should be, apparently to all orders in the loop expansion. But n equals 8 is the place where the dragons start. And so she had two approaches to trying to make progress on the symbol alphabet from the perspective of Flavic graphs and various constraints, solutions to equations C dot z equals 0, and also a new class of mathematics or brought to the attention of physicists called tensor diagrams. And in particular, the ones that were not quite arborizable, so they always had a loop left in the middle, they could be resummed in a particular way. And that resummation develops the square root letters that were seen in calculations at n equals 8 by Q bar, using the Q bar equation for the NMHV configuration. Anastasia also served as a rapporteur by announcing that 3 new orbits of n equals 8 letters have been found at 3 loops in the poster by Zhang. Apparently, these are predicted correctly by tropical geometry considerations. So now I'm starting to get close to the end, and I couldn't resist throwing in a few things that I've been working on with my collaborators, some of which are organizers of the conference. So I thought I would just briefly mention that as a segue from what Anastasia was talking about. She was talking about very complicated symbol alphabets. And I'm a simple-minded guy, so I like simple symbol alphabets. So recently we've been doing a bootstrap that has an extremely simple symbol alphabet. And it's sort of inspired by this Higgs production we talked about earlier, but we're not going to do it in the real world in QCD. We're going to do an analog of it in n equals 4 Super-Yang-Mills theory. And in the real world, you integrate out the top quark, and the top quark mediates the production of a Higgs from 2 gluons coming in. But this integral gives you an operator, which is essentially the QCD Lagrangian, and then the Higgs just injects some momentum. So in the n equals 4 world, we consider the form factor of an operator, which is in the stress tensor multiplet. And there's remarkable similarities between this form factor and the QCD one at 2 loops, which was recognized by Brandhuber and Travellini and Yang about a decade ago, based also on work by Thomas Germann and collaborators in QCD. And Claude also pointed out some of these connections. So the Higgs amplitudes are basically equivalent to matrix elements of this operator with multiple gluons, which are often called form factors in the amplitudes community. So we're going to look at the form factor of the stress tensor supermultiplet with 3 on-shell gluons. We could also have considered it with 2 on-shell gluons, but in that case, there's only one overall scale, the Higgs mass or this center mass energy of the 2 gluons, and that's just too simple. There's no kinematic dependence beyond some overall trivial dimensional dependence. We want a function of at least one variable, and this quantity is very simple. It depends on just 2 dimensionless ratios. Let's take a quick look at the kinematics of this process. There are 3 momenta, massless momenta, that add up to the Higgs momenta. If you square this relation and you use the invariant mass of the cross products with the momenta squaring to 0, you get this relation. So the invariance of any 2 pairs of gluons, if we divide them by S1, 2, 3, we can define some ratios U, V, and W, which are named that with malice aforethought. But U, V, and W have to add up to 1 now because we've divided both sides by S1, 2, 3. So we have a two-dimensional plane parameterized by U and V, and W, lines of W go like this. So there's also a W equals 0 line here. And so this is great because we can actually plot the entire kinematics literally in 2 dimensions. And another interesting thing is that these variables are not cross ratios, they're actually ratios, and they're the same set of variables you would have in QCD. So and the n equals 4 pure gluon amplitudes live in a different dimensionality from the QCD case. And whenever we need to bootstrap these things, and the reason we didn't try this earlier was because we didn't have any boundary data. But thanks to the work of Amit Sever and Alex Tumanoff and Matthias Wilhelm in these 2 papers, there's near collinear data that is sufficient to carry out this bootstrap. So we know what the function's doing here. And we also know what the function space is from a guess based on 2 loops. And at 2 loops, the underlying functions were defined or called 2D HPLs by German and Remedi. And they're basically the statement that every function has a derivative, which looks like this. And if you remember that W is 1 minus U minus V, and you know anything about the symbol, you'll see that the symbol alphabet has just these 6 letters. If you know about the hexagon function bootstrap, there are 3 more letters that we don't need to deal with here. So it's extremely simple. And our task is to identify as small a subspace of 2D HPLs as possible by hook or by crook and construct it to high weight. So I'm not going to tell you about any of that. There's no time, but I'm just going to tell you that it works like greased lightning or like magic. So with just these boundary input helpfully supplied to us by Matthias from his other collaboration, we were able to go to 5 loops. And with Omer Gerdigan, since this paper came out, we've been able to go to 8 loops. And so I just want to say that the new standard for publishing in planar n equals 4 is that you have to do 3 loops at a time, okay? So in case you can't wait for this paper, well, I gave 4 hours of lectures at the school, the MITP Amplitude games, and I sort of focused on this system because it's even simpler than the hexagon system. So if you were interested, here I just want to show you one plot because I love making plots, and it shows the remainder function, which anyway, it's a function you can define that characterizes the finite parts of the amplitudes, and it's a function of both variables u and v. But to make the plot, we set u equals 1, so we're living on this line here. And this function has real and imaginary parts because we're really in physical scattering here. And the imaginary part divided by the real value at 1 has this dependence on v. And you can see that the behavior is getting very uniform down at smaller values of v as the loop order increases, but it takes a little while for this to set in. And so here we go. We have a 8 loop result here, which is built out of weight 16 polylogs. And if you want to know how to plot weight 16 polylogs, ask me later. So now I just want to make a little short segue, and I wanted to mention that very interesting talk that was presented by Anna Spearing, and she discussed the transition between integrability and chaos in Super-Yang-Mills theories and the dependence on the number of colors. So in the planar theory, we all know, or those who work on it know, that it's integrable, whereas at finite values of n, the theory is not generally integrable for all sets of operators. So they studied the eigenvalues of very large systems of operators at 1 loop, and they compared the nearest neighbor spacing S, the distributions of nearest neighbor spacings, with a Gaussian orthogonal ensemble of random matrices. And that's considered a hallmark of quantum chaos. And that's this yellow curve here. So you can see that at finite values of the number of colors, you have this chaotic behavior of the level spacings. Whereas in the planar theory, you get integrability, and then there's a suggestion you should see Poisson statistics. And that's exactly what they saw. Now, I'm not trying to say that what we're doing is related in any physical way, but we view this as licensed to do statistics too. But we just have one amplitude. So what are we going to do? We're just going to do statistics on the coefficients of all the harmonic polylogs that appear in these functions. For example, on this nu equals 1 line, the number of polylogs goes roughly like 3 to the 2L, which is getting very big. And sorry, this one is 2 to the 2L. This one is not so big. It's only about 16,000 up here, it turns out. Anyway, you see that there's kind of a uniform shape to the distribution of all these harmonic polylog coefficients, which are all integers, by the way. I've just taken the log base 10 of them. And you can see how the centroid marches up slowly with the loop order. But there seems to be a convergence of the distribution here at large loop order. And then we went to the u equals 1 line. In this case, the numbers of coefficients grows faster. And we've discovered a new resonance here on the high side. So anyway, I'm just hoping it's not the 750 GeV resonance. No, I'm sure it's not that. Anyway, this opens up a broader question, which is that when you do some of these calculations, and I'm sure it's not just in these arenas, but in other areas of amplitudes, there's a huge amount of theoretical data that goes along with it. And the question is whether that data can be grist for a machine to learn what the patterns are. Because one thing's for sure is you can't stare at this list of numbers yourself and without going blind. And so it seems to call out for some machine learning approaches to amplitudes. By the way, there has been a little bit of machine learning applied to amplitudes. I may have missed some things, but I know that Simon Badger and collaborators, they used machine learning to try to approximate amplitudes. This would be to try to use it to get exact amplitudes based on lower loop information. If the machine would be able to propose to us the L equals 9 amplitude, we could probably check it, even if we aren't able to construct it ourselves. But that's probably for the future. Speaking of the future, in the few remaining minutes, I just wanted to make a few predictions. Nima told me that he had to go somewhere else, maybe. So I just want to say my first prediction is that totally magical and highly non-trivial results will be found in the coming years that even rival the amazing ones that were presented at this conference. That's prediction number 1. Also, there will be 3 new hedra discovered by 2022 to go along with the amplitude hedra, cluster hedra, surface hedra, binary hedra, halohedra. That's the number I could remember, but you may remember more. Also, Zvi will finally lose a bottle of wine. And finally, in the machine learning direction, the loss function for total magicality will be discovered. That will enable machines to put us all out of business. So I'm sorry about that last prediction, but you know, that's how things go. So I'm glad we were able to thank the organizers because they did this astounding work under difficult circumstances. Other people who did outstanding work under difficult circumstances include all the first responders and medical personnel who have been under extreme stress for the last 17 months or so. Also public health officials. I went for a bike ride on Sunday and I saw this picture of Anthony Fauci on a pole. So I know I'm in a blue state when I see that. And of course, the vaccine manufacturers. And thanks to all of you and almost everyone else for taking their vaccines and other precautions to try to keep the spread of this coronavirus down. And hopefully we'll lick it all, at least to the extent that we can move again, move about. So backed by popular demand is Greta Thunberg, She wishes to thank us all for not flying to Amplitudes also this year. We'll talk again next year in Prague. So thanks in advance, Yara and Carol, because I know you're going to do a terrific job putting on Amplitudes 2022. And that's all I had. So have a safe journey back to the kitchen, and thank you for your attention.
All right, well, let's all thank Lance for this overview talk.
Bravo, bravo.
And I welcome any people to raise their hands with questions or comments for Lance. And while we wait for that, I'll mention, Lance, you took the quarantining a little too seriously, since every time I've seen you on Zoom for the last year, you've been on Mars. So
yeah, I wanted to
you're
say
welcome to
about
come
that.
back anytime.
We have all these fires going on in California. I just decided the air was better on Mars. It's a little thin, but it's clean. There was a comment in the chat that I misattributed the poster, and the poster was produced not by Qi Zhang, but by his collaborator, Zhenji Li, who did, most of the computation. Thanks for that clarification, Qi Zhang. And congratulations, Zhenji, on some very nice work. We look forward to the paper.
So Lance, you made some predictions for 2022, but can I push you for any predictions for 2031 while we have you here?
Oh, 2031. Yeah, I don't know about 2031.
All right, we'll wait till the recording stops then.
Well, yeah, I mean, I really think machine learning will be used in amazing ways by then. That's 10 years from now. What else will we know that's not in that sort of in that direction? I don't know, the overlap with mathematics is going to become stronger and stronger, and I hope we have, you know, a much richer understanding of gravitational dynamics and putting together various ingredients in QCD and finding new areas to connect to, besides the ones we've traditionally done. David.
Yes. David?
Yes, thank you, Lance. I was actually moved to tears by your talk, which is a wonderful reminder of the things that I've heard in all the talks of this week. But I'd also like to add something, and that is to the collegiality of our community. I know there are rivalries, I know there are arguments, but at the end of the day, we're all trying to tackle hard problems. And we work very hard, and we tell other people what we've done, and they say we've worked harder than you, we disagree with you. But not only has it been a wonderful conference and organization, as you've applauded from Copenhagen and Penn State, and in the quality of scientific contributions and in the dialogue of participants, but it's also been a celebration of our basic commitment to mathematical physics, our sense that the questions that we're addressing are greater than ours. And you've captured that for me very wonderfully and very emotionally. So thank you, Lance.
Thanks for that comment. Yeah, definitely resonate with it.
All right, well, with that, let me suggest that we say thanks to Lance once more. And then I believe we actually have some closing words. We have one more call from Niels Bohr to close the conference.
Thank you, Professor Dixon, for that excellent summary, and thank one and all for joining us for this most exciting week. I should, of course, give my heartfelt thanks to all who made this conference possible. To the organizers, both local and advisory, who worked to ensure a smooth functioning event of manifest scientific quality. To the speakers, those discoveries serve as sure inspiration to us all. To the Pennsylvania State University, which stepped in with technical acumen to improve our most unusual format. To Ms. Elvekær, those organizational assistance has been truly profound. To the many young people of our institute, though their diligence gave us the means to both make available this conference to the world and to keep its record for long posterity. And finally, to the artists, those whimsy allowed me in this form to join in this activity. For all those who have contributed to this splendid week, shall we not give one more contribution of applause?
That's a speech by Niels Bohr.
All right, well, that's the conference, folks. Thanks everyone for